says, I'm very glad to introduce Professor Bong Lian from Brandeis University, who will lecture on the Riemann Hilbert problem for period integrals and recent applications.
Thank you. So let me begin by thanking the organizers of this conference for their invitation. It's both an honor and pleasure to speak in this great conference. All right, let me start. Let me start with this sort of big picture. So this talk will primarily be think of it as a study of the interplay between three subjects: algebraic geometry, physics, and the theory of special functions. But for today's lecture, I'll mainly focus on a couple of applications that goes in these two directions. One from algebraic geometry to physics, and the other from this to special functions. Okay? All right, let me first acknowledge my collaborator. Whoops. This clicker is fast. I get used to this. Okay, so these are my collaborators: Jingyu Chen, An Huang, Xingtong Yao, and Mingjian Xu. All right, so here's a, something is wrong. Something is wrong.
You can also use the manual.
I think I better stick to the manual thing.
Okay.
This thing.
So I think when you press it, you have to press it.
Okay, all right. Okay. Still trying to get a hang of this. Okay, so here's a plan for my lecture. I'm going to start by giving you an overview of the Riemann Hilbert problem. Now, of course, this is a problem that goes back to Riemann's thesis in the mid-1800s. So it's got a very long and glorious history for which I certainly don't have time to get into details in this lecture. But I will kind of focus on sort of a geometric version of this that it sort of emerged more recently, and go into how it applied to various problems in physics and in special function theory. So the first application I will talk about is a solution to something called the hyperplane conjecture in mirror symmetry, and the second application is to study derivatives of the zero set of generalized hypergeometric functions. All right, so let me start with the geometric setup. So consider a family which I call pi. The total space is Y and the base space is B of d-dimensional compact complex manifold. And I will name the fiber at the point B straight YB. So as it is standard, if you look at the K cohomology group of the fibers, they form a local system, which I'll call capital E, that is equipped with a Gauss-Money connection. And in this lecture, we will focus just in the case when the cohomology degree is the middle dimension D. Now, the dual bundle of E is a bundle whose typical fiber is the homology group in the same degree. And I'll denote the dual connection nabla. And thanks to Poincare pairing between the cohomology group and homology group, it induces a pairing at the level of the sheaf of sections. And the local parallel sections of the homology group bundle is nothing but just given by the homology group in the neighborhood of a point B by Riemann theorem. All right, so let me introduce something called the period sheaf. So let's fix a global holomorphic section omega of the bundle E. And with this choice of section, I want to pair this section with every parallel section of, namely the homology group bundle. And so this pairing gives me a local holomorphic function in the variable b. So formally, this is just the integral of this omega, which pointwise is just a form of middle dimension, integrate over the cycle gamma. So such a local analytic function will be called a period integral of the family Y. It's not moving. Okay. 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 So here's the problem. We want to construct an explicit, complete linear PDE system, which I generically call tau, for the period sheaf. That is to say, we would like to find a PDE system whose sheaf of local solutions, so tau, agree with the sheaf of period integral we started with. Okay. So why are we interested in such a problem? Well, for one thing, this period integral have been of interest to both physicists and mathematicians for a long time, especially their explicit power series expression. So one way to use the solution to this problem would be to solve the PDE system to obtain power series solution. The second thing that one might apply this to is to understand monodromy of the period integrals from knowing the explicit solution. And the third and more recent application of this is, of course, mirror symmetry, as it is now a well-known story that you could use period integral to compute, to count rational curves in algebraic variety. I won't have much to say about the first two in this lecture, but I'll mainly focus on the third. And the fourth application, which is that once I have these explicit information about periods, I want to be able to say something about them as special functions, because these are generalization of classical hypergeometric functions. So for example, one might want to know something about their singularity, their monodromy invariant zero set of their derivatives. Okay, so one particular situation that is of a lot of focus in recent work is the case when one is interested in hypersurfaces in a fixed ambient smooth projective variety X. So we will start with a fixed very ample line bundle L on X and consider the universal family of hypersurfaces of smooth hyperplane section of this line bundle L. And we will focus in this lecture mostly in the case when the hypersurface is Calabi-Yau and the ambient space is Fano. Now, a lot of what I will say actually applies also to Fano hypersurfaces and general type hypersurfaces. Okay, so the first thing to do is that we would like to choose a section of the bundle E that we started with. So let's recall that the bundle E has the standard variation of hot structure of weight D given by the filtration denoted by Fp of E. So here's a way to get a section. So it turns out that for any Fano manifold, there exists a canonical section of the bundle E which trivializes the first term of the filtration. So here's, without going into detail, let me just sort of give you an example to illustrate this. So if you take the projective space, then omega is just a familiar Poincare residue given by this formula here, where omega written in the homogeneous coordinate is given by this, and f is simply the universal section. So at each point, this is just a degree n+1 polynomial. And residue is just the usual Poincare residue. The upshot here is that this construction can be generalized to any complete intersections on a Kähler manifold. OK, so let me now return to the Riemann Hilbert problem for the period sheaf. So I want to introduce an idea which sort of partially solved the Riemann Hilbert problem. So let me start with some notation. I have these data. I start with a complex algebraic group G, and X is an n-dimensional smooth projective G variety over the complex number. Okay. Notation. So let V check be the space of sections of the anti-canonical, and let F be the so-called universal section. So this is a bundle value function which capture every single section at each point. Let U be the universal complement, namely the complement of the zero set of the universal section in V check cross X. And I introduced the vowel algebra, which I call dV check, on the affine space V check. So if you choose a set of linear coordinates on the vector space V check, this is just nothing but the ring generated by p+1 coordinate together with the first derivatives. Okay, so now the goal is to get a differential system that annihilate these period integrals. So first, because you have a hypersurface by the usual Giesen sequence, you can rewrite it as an integral in the ambient space of this rational form over a cycle in the complement of the zero set of F. So this is the cartoon picture, and C gamma is the tilt over the cycle gamma in the normal bundle. Okay, so a couple of three observations. So if you look at the inverse of the reciprocal of the universal section, which is a function defined on U, and you look at the cyclic module, cyclic D module, generated over the structure sheaf OU. So look at this sheaf. So this turns out to be a cyclic module of dV. So now you look at pick a differential operator that annihilate the function f 1 over f. Now, because differentiation commute with integration over the cycle, p moves inside and annihilate f, because omega is a sort of a constant form. So every differential operator that kill the function 1 over f automatically kill the period integral. So what you get is a set of geometric constraints. I denote by the set the ideal that annihilate 1 over f as Jx. Next, X is started off as a G variety, so the algebraic group G acts on it. And so for every element of the Lie algebra of G, you get a vector field induced on the vector space V check. So V check is now a linear representation of the Lie algebra of G. Now, this vector field automatically annihilates the period simply for symmetry reason. After all, the integral here is nothing but a Poincare pairing. So any symmetry of the ambient space will automatically annihilate this Poincare pairing. Moreover, notice that omega over f has a homogeneous degree of -1. Because f lives in the denominator, it has a homogeneous degree of -1 in the coordinate of v check. And therefore, the scaling group Gm on this will induce an Euler vector field that annihilate the period integral as well. So together, they give you a bunch of symmetry operators. So these are all first-order differential operator annihilating the period. I denote by Zg collectively this symmetry operator. Okay, so here's the definition. I define the cyclic D module given by this quotient, where the left ideal I mod out is the symmetry operator generated by the symmetry operator together with the Euler and the annihilating ideal of 1 over f. So just by observation 1 to 3, automatically this left ideal will annihilate all the period integrals. And so this D module will in fact be a partial solution to the Riemann Hilbert problem. We called this D module a tautological system. All right, so here's the summary of what I just said. So this is a result that goes back a few years ago with Song, former student of Yao, and a follow-up paper of myself and Yao. So the statement is that the period of the family Y form a local analytic solution to the tautological system introduced in this definition. Okay, next I want to give you two important classes of examples. So first, let's take X to be a smooth toric variety with a dense torus, which I call T, acting on X. Then in this case, the tautological system reduced to something that has been known for a long time. So in fact, this system was introduced by Kapranov and Zelevinsky in a series of papers leading up to the paper in 1990. So the system can be very explicitly described by this formula. So the constrained differential operator are all binomial. They are indexed by a vector in a certain sublattice of Zp plus 1. And together with the symmetry operator I introduced earlier. So in this case, because the symmetry group is chosen to be T, this is now an abelian Lie algebra. So the first order differential operator are parameterized by an abelian Lie algebra. So what is this sublattice here? Well, the sublattice here are nothing but the lattice of relations defined by this equation of the weights of the T action on this vector space. Recall that this vector space is just the space of anti-canonical sections of X. So this is one case, and a very important one. This is a second case. Take X to be a G-homogeneous variety. And then in this case, one also has a very explicit description of the tautological system. Namely, aside from the symmetry operator, which is coming from the group G, the constraint operator are very simply described by these second order, or generated by this second order constant coefficient differential operator. So what are they? Well, you take the quadratic Casimir operator of the Lie algebra G. So assume G to be, say, reductive. Take the quadratic Casimir. The quadratic Casimir acts on the second symmetric power of V check. So think of this differential operator as forming a basis of the second symmetric power of V check. So this operator CG acts on this space. Now it turns out that this operator, the second Casimir, acts diagonalizably, and there's a distinguished eigenvalue such that if you project it out, what remains is give you precisely the space of generator of the constraint operator of tau. And this is, with a little bit of work, this actually just follows from a very old unpublished result of Burt-Costin in '76. Okay, so here's a more recent theorem. So this is a joint work with Spencer Block, Huang, Srinivas, and Xingtong Yao, and a later paper with Huang and Xingwen Zhu. So the statement is this: if X is a G-homogeneous variety, then you have the following very simple criteria for tau being complete. So tau is complete if, and namely, the solution sheaf agree with the period sheaf, if and only if the middle primitive cohomology of X is 0. So this says that this cohomology is the only obstruction to completeness. Now, one might want to ask the same question about the case when X is a toric variety, in which case we just introduced the GKZ system, tau GKZ. Now, it turns out that in this case, unfortunately, the system is never complete. So, so the problem, therefore, is that you would like to at least try to describe the period sheaf as a subsheaf of the GKZ system, the solution sheaf of the GKZ system. How is it sitting inside? Then that brings me to the first application I want to discuss. So this the solution was proposed in 1995 thanks to mirror symmetry. So the solution is actually inspired by mirror symmetry. So let me, without going into the history of mirror symmetry, let me just sort of introduce enough notation so that I can state the conjecture and explain the recent proof of this conjecture. Okay, so what is the initial data? Well, so this is the mirror symmetry in the setting of toric Calabi-Yau hypersurfaces, which was formulated by Batirev and Borisov about in the early 90s. So the initial data is that you start with a pair of integral reflexive polytope in Rn, and associated to these two polytopes is a pair of fans defined whose cones are nothing but cones over the faces of these polytopes. So once you have a pair of fans, you now have a pair of toric variety. This pair of toric variety has the property that they're delta regular Fano toric variety. That is to say, the generic Calabi-Yau hypersurface intersect with each T orbit transversally. So the upshot of this is that whenever you have a Kreppen resolution of this variety, then it automatically gives for free a Kreppen resolution of every hypersurface a generic hypersurface inside of X. Okay. So in other words, you do the resolution for the whole family all at the same time when you have this delta regular condition. All right. Next, we assume that this pair of polytope admits a regular projective triangulation. What that means combinatorially is simply that as a polytope, each one admits a unimodular triangulation, meaning each n simplex has volume 1 or normalized volume 1 and has a vertex at the origin. Okay, so under this assumption, each of these toric variety X and X check now admits a projective resolution. Okay, so this would be what one call a pair of mirror toric manifold, and sitting inside this pair of manifold are a pair of mirror Calabi-Yau manifold. So this was the insight of Batirev and Borisov. Okay, a little bit more notation. So I'm going to first call the projective resolution and put a tilde in it. Okay, and so for one of them, so I'm going to start to be a bit biased, and I will mainly, well, the conjecture is going to involve both manifold, but much of the geometry is going to occur on the x tilde side, at least for the focus of this talk. All right, so I'm going to denote the T-invariant divisor of x tilde as d1 to dp, and I call their negative sum d0. That turns out to be just the anti-canonical divisor of x tilde. Let m plus to be the set of all integral points in the Mori cone of x tilde. So here's a O theorem that goes back to GKZ and a generalization due to Adolphson. It says that the universal family of Calabi-Yau hypersurfaces in x tilde check. So for this family, the solution sheaf of GKZ has a rank that is exactly given by this very nice formula, this normalized Euclidean volume of the polytope delta. Okay, so you know the exact number of solutions of this GKZ system, which, as I mentioned, is never complete. So the problem is to try to extract the part that is relevant to period integral. And so this was a way to extract such a solution is proposed in '95. And so let me now explain how the extraction works. So you look at a neighborhood of a certain point at infinity, so namely this neighborhood. Recall that my A naught are nothing but just the linear coordinate on the space of anti-canonical section. A naught play a special role. It's a particular coordinate. And I want to look at the place where it is sufficiently large. So in this neighborhood, I want to introduce something called the B series. So thought of it as a cohomology value function defined on this open set. So explicitly, it's simply given by this formula. Okay, so let me explain the formula. The gamma here is the usual gamma function, except that the argument you put in there are formal symbols. So this should be thought of as a formal power series in the symbol D naught. Okay? D naught will acquire a meaning here when you specialize it to this cohomology class D naught. So because this ring, the cohomology ring is nilpotent, it makes sense to expand this as a power series, and it will have finitely many terms in the power of D naught. Likewise, in the denominator, the Di as a toric divisor. So if you expand this as a formal power series in Di, this will be a finite expression. Okay? So this is a formal power series, but because I'm in this domain, it turns out that this function actually converges in this open set. So I have an analytic function that takes value in this nilpotent ring, which I call B of x tilde. Okay, so here's the building up to the hyperplane conjecture. So in '95, it is already known that the period sheaf is a subsheaf, as I mentioned earlier, of the solution of GKZ. So the question is, what about the solution sheaf itself? How do we describe the solution sheaf? Well, as it turns out, the B series is precisely the function whose scalar component generate the solution sheaf to GKZ. In other words, this explicit power series gives you the full general solution to this PDE system tau GKZ. Okay? So the problem is now to extract the period integral from this B series. And that brings us to the hyperplane conjecture. So the hyperplane conjecture says the following. The period sheaf is of the family of Calabi-Yau in X check tilde is in fact given simply by the cup product inside the cohomology by the canonical divisor of X tilde. So because B tilde is a cohomology value function, when you cup it, this is still a cohomology value function. So you take the scalar component and you generate a local system. The claim is that local system coincides with a period sheaf. Okay? Okay. I will refer to the right-hand side of this equality conjectural equality, the cup product sheaf. So here's an example that goes back to the famous paper of Candelas and company in 1991. So if you take x to be CP4 and x check to be this finite quotient of CP4, this is a so-called mirror CP4, and you run through the machine that I just talked about earlier in the few transparencies earlier, you can then immediately write down the B series. And the B series is just this nice function. H here is the hyperplane class of CP4, and Z here is this combination of the coordinate AI. And the cup product sheaf in this case turns out to exactly agree with the rank 4 period sheaf of the so-called mirror quintic threefold, as predicted by the hyperplane conjecture. So as most of you know, this function is responsible for a lot of excitement in algebraic geometry for the last 20 years. Okay. Now let's sort of change the problem just a little bit. Let's switch the role of x and x tilde by flipping the two manifold around. Okay, like that. Just change the role. Well, so in this case, you still get a mirror pair because the mirror pair is sort of reflexive. Then the hyperplane conjecture described now a completely different problem. It described the rank 204 period sheaf of the quintic rather than the mirror quintic. So in this case, because you have a sheaf that is so large and you have a pretty bewildering looking PDE system, checking this conjecture is no longer straightforward, right? So in the last couple of talks where Mu Tao talked about 10 functions, that was already bad enough. Here you have 204 functions. Okay. So that example I just gave you already indicates some of the difficulty. But let me mention, sort of in more general terms, what the gist of the difficulties are. So there are sort of three main points. So first of all, even though the initial data I started with is a pair of Fano singular toric variety, x and x check, in order to make sense of the hyperplane conjecture, one has to make several choices. In fact, you have to make a choice of the Crepin resolution. It turns out that typically, given an x, there are really a huge number of Crepin resolutions. They are all, of course, birational to each other, but they are combinatorially very different choices. Okay, so that's the first difficulty. There are just too many data you have to keep track of. The second difficulty is that none of the Crepin resolutions are Fano, even though you start with something that is Fano. So it makes it hard to compute cup product when you're cupping with something that is that is not an ample divisor. Okay, and the third difficulty is that even the period sheaf itself. So the conjecture involved two sides. One involved the cup product, the other involved an analytical object, the period sheaf. That period sheaf was not understood at all, even for the quintic case. These 204 functions until just 3 years ago. So that kept the conjecture unsolved for more than 20 years. Okay, so what is the strategy? Well, the strategy isn't exactly new, but it turns out that the tool available to carry out this strategy was only available only in the last 3 years. So the strategy was that, well, okay, so you have something that is not Fano, right? Well, blow it down to something minimal, and sort of forget all the combinatorial choices, and try to use a resolution-independent way to describe the cup product sheaf. So that's a nice idea. All right, so to carry out this idea in this talk, I will try to explain the sort of the main step by sticking to this basic example. This is already sort of, all the difficulty is already showing up in this basic example. All right, so here's the first step of the argument. So first, I want to give a D-module description of the period sheaf, sort of replacing this analytic object by something algebraic and more manageable. Specifically, I want to find a complete D-module. Okay, so that reminds us of the Riemann Hilbert problem for the period sheaf. So again, generically, I'll call tau. So I want to find such a tau so that it's complete, so I get this equality, and so that I a priori know that my, my cup product sheaf is also sitting inside as a subsheaf. So I have some way to anchor, sort of connect these two things, right? So that's the first step. All right, so and this step turns out to be not too hard, and it's been dealt with very recently. So it turns out that you can now modify the GKZ system by replacing the torus by the full automorphism group. You know, I call alt here. So the tautological system still makes sense. All you're doing is you enlarge the symmetry group. And I'll call the enlarged system tau E GKZ for extended GKZ. So as it turns out, in this case, for Pn, the completeness theorem I stated earlier with Bloch and company and Huang and Zhu and Yao, we obtained the statement that this equality holds, which means that I get this equality. Okay, so tau here is now tau E GKZ. So I obtained an explicit differential system for my period sheaf. So now I've translated this analytical problem into this algebraic object. Next, I want to show this inclusion. Okay, so this is a more recent result with Mixian Zhu. So the statement is that for any pair of mirror, mirror pair in the sense of Batyev, Borisov, the cup product sheaf is alt invariant. So that translates into the statement that the cup product sheaf is a subsheaf of the period sheaf, and hence this inclusion. So that takes care of the first step. So the second step is, well, you want to be able to, you do everything here. You want to be able to, well, you blow it down. You want to be able to come back and forth, right? So you want to have some way of comparing these two spaces. So after all, we're trying to prove the equality between these two sheaves. We already have one inclusion. We're interested in proving the opposite inclusion. So that, of course, reduces to, because the B series takes value in the cohomology group, and every component of the cohomology group is involved in the B series. So this shows that the rank of the cup product sheaf agree with the rank of the cup product by the anti-canonical divisor. So proving this inclusion reduces to proving this numerical equality of ranks. Okay. So the question is, how do we achieve that? All right, so if you knew that the anti-canonical, the canonical divisor is ample, then you can apply Lefschetz, and the game is over, right? You can just compute it using Lefschetz. Unfortunately, you're out of luck most of the time, because these Kerpen resolutions usually are not final. Sometimes they are, but usually they are not. In fact, typically they are not. And so Lefschetz can fail. All right, so the idea now is to compare the cohomology group under the Kerpen resolution by expressing the cupping with the anti-canonical divisor of the blow-up in terms of the cup product downstairs. Downstairs, this canonical divisor is ample. So you try to compare, express this guy in terms of this guy on the singular space, and the hope is that you're able to use the ampleness of this to compute this and translate into information about this. Okay, so you need a couple of technical lemma to do so. So first, it's a standard result that if you look at a Q sheaf or in the derived category that is bounded below on a variety A. And if you have a morphism from A to B, then it automatically induces an isomorphism of hypercohomology of the Q sheaf F and the derived push forward of F. So now this gives you a way to compare hypercohomology on two different spaces under this morphism. Okay, so that if you apply this to this Kreppen resolution and assume that your Q sheaf is actually a constant sheaf with concentration in one term, then you get this commutative diagram. So that means you now have translated the cup product on the ordinary cohomology of the blowup into the cup product of the corresponding divisor downstairs on hypercohomology. Okay? So computing rank here now becomes the problem of computing rank on this singular space. Okay, so for that computation, we have to rely on the famous theorem of Bernstein, Beilenson, Lian, and Garber, the so-called decomposition theorem. More specifically, we need to apply the toric version of it, which was not available until 2014 due to Di Cataldo, Migliorini, and Mastada. So the statement of their theorem is the following, that if F is a toric vibration, then the derived push forward of the intersection complex on the domain can be decomposed in terms of intersection complex of certain closed toric subvariety of the target B. Okay? All right, without going into too much detail, the upshot here is that this is a direct sum of intersection complex of lower dimensional variety with some multiplicity, which I call S, and with some dimension shift given by an integer. Okay? These lower dimensional variety are nothing but closure of the T orbits of the toric variety B. These T orbits are parameterized by cones of the variety of the fan of the variety, sigma B. Okay, so here's a corollary of the DCMM theorem, that the hypercohomology that we're interested in of this derived push forward sheaf can be decomposed as the intersection cohomology of these closed subvariety V of sigma. Again, with some multiplicity and with some degree shift. And as a consequence, you can apply a further result of DCMM to compute this multiplicity and translate into a computation of the rank. And the reason is because this decomposition is not just a decomposition of vector space, but it's a decomposition of module over the topological cohomology group of X. So that way, you can now, because cupping it is an operation on from the cohomology group, you can now use this cupping operation and operate on both sides and get the rank by computing the rank on the right-hand side. Okay? And as I said, you have this closed formula. So the rank of cupping with Y is now given by this sum over some multiplicity times this rank on the individual pieces on intersection cohomology. The delta sigma is nothing but the total multiplicity. Okay, so the last step of the proof is to compare the rank. So what's left to do is to compute this total multiplicity. And it turns out DCMM also had an explicit formula of that. So you need to do a little bit of hard left sheds, and together, so you're able to compute the left-hand side, the rank of cupping with Y, and therefore the rank with the cupping with Y tilde. On the right-hand side, you also need to be able to compute the rank, and that we have to rely on this joint result with Spencer Bloch and company. So thanks to the completeness theorem, this rank is now also known. So by comparing the rank, you conclude the proof that the two ranks are equal. And therefore, you get the equality between the period sheaf and the cut product sheaf. All right, since I'm short of time, I'm going to move along. All right, so now let me spend the remaining minutes to talk about the second applications of the Riemann Hilbert problem. So this is about studying the monodromy invariant zero set of derivatives of periods. Because these periods often arise as hypergeometric functions or generalized hypergeometric functions, this gives you new interesting information about derivative of hypergeometric functions. Okay, so the setup is that as before, I start with a Fano G variety with finitely many orbit. And consider the period sheaf of the universal family of the Calabi-Yau inside X. And I will assume that we have a complete tautological system so that I have this equality. So the point here is that I can now exploit this equality, namely the solution to the Riemann Hilbert problem, to make use of whatever I can find out about tau to say something about the period sheaf. So here's the problem. I fix a homogeneous differential operator in the Weyl algebra. I'm interested in describing the zero set cut out by the local system by simply taking the derivative and apply to this period, this local analytic function over the base of my family B, okay? So this is a local system, so it makes sense to talk about their zero set, right? And because this is a local system, this set is actually monodromy invariant. Okay. So what can I say about this set? So in general, not much. Now, because I impose that this differential operator be homogeneous, you can say that, well, they are scaling invariant. So you can talk about projectivizing them inside of V check, this vector space V check, and take their closure inside of PV check. So what you get is some closure of some analytic subset of PV check. Okay. Okay. So the first statement that you want to know is, well, whether or not this closed set is actually an algebraic variety. The answer, happily, turns out to be yes. It turns out that because I have a complete, again, thanks to the solution to the Riemann Hilbert problem, I have a complete holonomic system. I could use that to sort of control what kind of the limit points of the set n delta, and one can show that the limit points are also defined by analytic function, and therefore by Chow's theorem, the closure will be guaranteed to be a projective variety in PV check. So for every differential operator delta, you get a projective variety. Okay, so what can you say about this variety? Again, in general, not much yet. I mean, this is still a topic that is in a very nascent development. Disappointingly, in general, this variety could turn out to be empty. However, based on just experimentation with a few known examples, it turns out that it seems very likely that if you assume delta to have constant coefficient, okay, meaning it doesn't live in the full Weyl algebra, but live in this ring of polynomial, ring of constant polynomial differential operator of homogeneous degree D, then our expectation, just again based on example, is that this projective variety is non-empty. And later I will show you an explicit example connected to classical hypergeometric functions where we show that this statement is true for generic delta. Okay, here's a baby example where you can work out literally everything by hand. Okay? So take P1. So in this case, the universal family of Calabi-Yau is just the configuration of 2 points, 2 different points moving inside of P1. Okay? And you could compute the period sheaf explicitly. It's generated by a single function. So this is a sheaf of rank 1. And the function that generated is this function with monodromy plus or minus 1, given by the 1 over the square root of the discriminant locus of a quadratic polynomial in 3 variable. So given by this polynomial. And for generic delta, you can literally work out, case by case, this projective variety. It's nothing but a plane curve of degree d. Okay? Okay, so here's the vanishing criteria. So how do you tell when a point is in this vanishing set delta? Well, it turns out, so again, this is a recent result with Chen, Huang, and Yao. It says that, well, if you compute the formal derivative of this formal exponential e to the f, remember f is the universal section, and delta is the differential operator I chose. So you could compute formally this derivative, and then you evaluate this formal derivative at a point B. If you could show that this vector end up in this vector space, and I'll explain the notation in a moment, then you guarantee that the point is in the 0 set, and vice versa. And what is this vector space? Well, so here, so let me go down to one more bullet point. So the vector space is defined as follows. R here is the projective coordinate ring of the manifold X. Remember X come with a very ample anti-canonical. So you can embed it inside of PV check. And this is the coordinate ring. So R denotes that ring. And what about Z check? Well, remember I introduced the module Z earlier on the vector space V. Z check is just the dual module. So Z check now acts on this ring R together with this multiplied by this formal exponential. So this is just the sum of all images of this vector field on this vector space. So in principle, you can write down a basis of this vector space, and so this become so you can literally check by hand when a given point is in this vector space. I mean, at least in principle. Okay, so this gives you a sort of a linear algebraic way to determine membership for this 0 set. Okay, next I want to apply this to a particular example. All right, so that brings me to P2. So let's go back to a little bit of classical theory. Everybody knows that the period of elliptic curves in P2 form a rank 2 local system in the so-called J plane, right? J being the J invariant of elliptic curves. And this rank 2 local system is governed by the Weierstrass-Picard-Fuchs equation. So you could go to Wiki and find that this equation is written there. Okay, so this is known for over 150 years. Okay, so for those of you who are closer to hypergeometric equation, you could actually translate this equation into the ordinary Gauss hypergeometric equation by simply a simple change of variable from J to Z, okay? Where J is expressed as a certain rational function of Z. So under this rational change of variable, this equation is nothing but the F21 of Gauss hypergeometric equation. Okay, so now I want to give a modern interpretation of this setup. Namely, recall that we introduced the extended GKZ system earlier. So I want to specialize that to this particular case, where the target space is P2. In this case, it turns out you could lift this differential equation to a tautological system as follows. Namely, when you consider the universal family of cubic curve and P2, recall that the completeness theorem specialized to this case, because in this case, tau GKZ is complete. So in this case, the period sheaf is therefore governed by tau E GKZ, okay? And we have explicit formula for tau E GKZ. So this lifting could be thought of as given by a base change. So what is this explicit base change? So in this case, V check is 10-dimensional. So every point is given by 10 coordinate, which I call B0 to B9. The base change is given by the map sending this vector B0 to B9 to the J invariant given by this well-known ratio. So the G2 and G3 are the standard Eisenstein series of weight 4 and weight 6. So this gives me a point in the J plane. Now, what is this G2 evaluated at B? Okay? Well, that's given by the following. So you compute G2 of B and G3 of B as follows. So the cubic curve YB correspond under this base change to the usual Weierstrass form given by this. So G2 and G3 are nothing but the coefficient of the Weierstrass form. And it turns out that these two, again, it's known that the Eisenstein series can be expressed in terms of a invariant polynomial of the group PGL3. So these invariant polynomials are degree 4 and 6, and they're actually known classically as Ehrenhall invariant polynomial. And their formula are known explicitly. So degree 4 polynomial has about 60 terms, and degree 6 has about 100 or so terms. Okay, so here's a proposition. Under the base change, the solution to this equation, the Weierstrass equation, and the solution to the extended GKZ system, this tautological system, are precisely given by this relation. So for every solution phi of this, you get a solution to tau by just rescaling by the Eisenstein series to a power of 1/4. Okay. Next, I want to use this to describe or give some information about this projective variety n bar. So here's a corollary. For generic delta, the projective variety, this projective subvariety in this case, P9, is non-empty and has dimension 7. Okay, let's see. I am kind of short of time, so I'm going to skip ahead. It allows me. Okay, but I want to highlight one point of the argument. The key step of the argument is to translate this membership condition using the vanishing criteria I gave earlier. Namely, you can now translate it into this equality. So B is in delta, if n delta, if and only if the delta operator can be expressed simply like that, given by this V check acting on the universal section evaluated at B. So notice that this is a linear equation. It's linear in B, linear in X, and it's linear in delta. Okay? Okay, so the point here is that you can actually now turn that linear equation into a way to compute the vanishing ideal of n delta bar. Namely, that equality now translate into this equality, which is linear in the coefficient of delta, okay, which I call lambda, and the coefficient of the universal section, which I call Bi, and the coefficient matrix, which I collectively call MB. MB is a matrix of certain size, whose entries are linear in B. So what you get is a linear equation of this sort. So that membership condition now translates into equal rank condition. So not only that these equations now give you an algebraic set of equations for the algebraic variety n bar, it gives you a stratification. So for each rank of both sides, you get sort of a stratum of this algebraic variety. Okay, so and you could at least in this low-dimensional case, you could carry this out using a computer and use this equation to compute the equation for n bar. Okay, let me stop here. Thank you.